Welcome, everyone. My name is Anu, and I'm a rising junior at Northwest. Our speaker today is Lara Ojha. As Anjali mentioned, Lara has been flying engineless gliders since she was 15 years old. She has a private pilot's license and several flying badges from the Soaring Society of America for completing challenging flights. Her love of aviation and passion for material behavior fuels her quest to tackle materials limited problems to push the boundaries of aerospace and engineering energy industries. For the past 3 years, Lara has conducted research at UVA on environmentally assisted cracking of aluminum alloys for industries, US Navy, and most recently, the International Space Station. She also works with Mechanics of Materials Lab at Oxford, studying the characteristics of hydrogen embrittlement in additively manufactured stainless steels. She is currently an engineering consultant at MPR Associates working on design, operations, material degradation, federal regulation, manufacturing, and global supply chain for domestic and international clients in the nuclear sector. Welcome, Lara. We are so excited to have you speak for us today.
Thank you so much, Anu, Pranav, and Anjali, for having me here today and for that really nice introduction. Hello, everyone. My name is Lara Ojha. Today I present to you on the wings of materials, where I'm going to attempt to explain what it's like being a pilot, as well as introducing the field of material science. So while these seem like relatively disjointed topics, I am going to attempt to blend these two passions of mine, as well as go through some of the opportunities that I've had being a student at university to explore the field of material science. These include conducting research in corrosion, hydrogen, and also working in the nuclear industry as an engineering consultant. To begin, a little bit of an introduction about me. I was born in Sydney, Australia, and my mother is from Australia and New Zealand. My father is from Darjeeling in India. I have a younger brother as well, and we grew up in the DC area. So I come from a very international family. And as I mentioned earlier, I'm a fourth year at the University of Virginia. I was lucky enough to receive the Jefferson Scholarship, so they have been funding my university education, where I've been studying material science as well as doing a minor in business. And I have been flying engineless gliders since I was 15 years old. So before diving a little bit into what it's like being a pilot, I know a lot of you are in middle or high school, and I wanted to give a quick overview of what my education was like before coming to college. So I went to elementary, middle, and high school in Montgomery County, Maryland. And the middle and high school that I went to were math and science focused programs. So math and science were subjects that I knew I was always interested in. And those schools gave me access to a lot of resources that helped me explore those interests. Two of the things that I did in high school that I think were really important to the development of my interests and the start of my career were first, the summer after my sophomore year in high school, I decided to take classes at Harvard while living in Boston in linguistics and anthropology. And you may be thinking, linguistics and anthropology has almost nothing to do with engineering. Why would you do this? This is because I was just interested in these two subjects. I'd read a lot about them, and I decided that I wasn't going to pursue a career in them, so I might as well take the time now before I get serious and go into college to study engineering to just have fun and explore these topics. I'm really glad that I had these opportunities because I learned a lot about how linguistics and anthropology are about solving puzzles and are actually more applicable to science and engineering than one would initially expect. So I've kept in touch with the subjects, even though I'm probably never going to be a linguist or an anthropologist. But I would encourage you while you're in middle school and high school to just explore all of these interests. The other thing I did in high school was the summer before my senior year, I worked as an engineer during an internship at NASA. This ended up being during COVID, so it became more of a software engineering internship that I had to do from home, but it was still a great experience. I got to work on calibrating detectors for a small satellite called BurstQ, which you can see a picture of on the bottom here. And actually on the next slide, I'll show a little bit of visual rendering of what it looks like in orbit. There we go. I'll just talk over when this video is playing because there's no sound in this video. So this is a small satellite that detects gamma rays from black holes. And in order to provide more information about how black holes behave, when I was an intern, I helped calibrate equipment for detecting these gamma ray bursts. And it's powered by solar power, and it was actually launched earlier this year. So that was a great experience, and it was really fulfilling to see, even years after I stopped working for it, it actually got launched. And something that I worked on is in space. So you can engage in these kinds of things while you're still in high school, which is very exciting. And let me try and get to the next slide. Okay, so now let's talk a little bit about gliding. So all of you know what a regular plane looks like. And you know that it has wings that help it stay in the air, and it has an engine that helps push it forward. So how do you fly a plane that doesn't have an engine? The answer is you need a plane with an engine to get you up in the sky initially. So as you can see on the bottom left, in order to get up without an engine, you are attached via a rope to a plane that does have an engine, and you are essentially towed up. You fly information up to as high as you want to be, and then you pull a release that cuts you off from the rope, and then you fly around as you normally would. But the difference is that instead of using an engine to stay up, you use atmospheric lift. So the atmosphere is a very complex system. There are parts of it that are going up, and there are parts of it that are going down. Some of the parts that are going up are called thermals, which are columns of rising hot air. So as you can see in this picture at the bottom center, if a glider is flying around and finds this column of hot rising air, it'll then circle around in it to gain altitude, much like a plane would just turn on the engine to gain altitude. So that is, you don't need an engine to fly a plane. You only need the engine to get up there in the first place. I don't know this. Hopefully I can play this video for you. Yes, okay, so this is a video of one of my takeoffs. So you'll see that this is the code plane, and you'll see my plane actually into it. There we go. And you'll notice the glider is much lighter than the tow plane, so it takes off first. That's because, of course, we don't have a very heavy engine. We don't have an engine at all, so it's a much less heavy aircraft. And there you go. As the tow plane takes off, so I also take off behind him and then have to follow very closely behind the tow plane. So there we go. So a little crash course on how to fly a plane. And how it differs from how an engine plane differs from flying a regular glider. So the diagram on the top right shows you the 4 forces that have to balance to fly a plane. The force that keeps the plane up is called lift. The force that cancels out lift is the weight of the plane, or gravity. The force pushing the plane forward is thrust, which in a regular plane is provided by an engine, but in a glider is actually provided just by gravity, because the plane is slightly tilted down, so you're always being pulled down, and the horizontal component of that pull is what pushes you forward as well. And then all planes have drag, which is essentially caused by the shape of the plane or surface roughness. The diagram on the bottom illustrates what's called Bernoulli's principle, which is what generates lift in any aircraft. The shape of a wing is called an airfoil, and the way that it's shaped as air passes over the wing and passes under the wing the air that passes over the wing has to travel faster in order to meet the air traveling under the wing at the same time. When air travels faster, it has lower pressure, so that generates a low pressure region above the wing and a high pressure region below the wing, and that pushes the wing up. So this is how all planes stay up. And then in order to turn and maneuver, we have 3 different axes of rotation. So you can turn this way, you can roll, and then you can also pitch forward and back. And that's how you control where you want to go. So how does one train to become a pilot? I joined a gliding club in 2018 when I was 15 years old. A club, the way that gliding clubs work essentially is that you pay a membership fee, and with that fee, you jointly own aircraft that are held by the club. And in return, you volunteer to help clean the aircraft, you help with ground operations, but importantly to me is when you join a club, they have volunteer instructors. So instructors who are very experienced will volunteer to teach you. Instruction is normally one of the aspects of flight training that's very expensive. So this is one of the advantages to starting with gliding rather than with powered aircraft. So I joined the club. I got an instructor who was an extremely experienced pilot, and you start going up on flights, learning basic skills, how to take off, land, completing, etc. In parallel, you're also doing a lot of studying of the theory behind aviation. So that includes aerodynamics, but it also includes regulations. So the rules that you have to abide by, generally because of the Federal Aviation Administration, weather patterns, maintenance, operations of a flight line, etc. So the first step into becoming a licensed pilot is then taking the FAA written exam, which tests these concepts and skills that you have been studying throughout your flight training. Then you do a practical check ride, which is like a driving test, essentially. The FAA sends an examiner to fly with you, and they will make sure that you're able to do basic skills, but they will also try and mess you up, because one of the most important things about being a pilot is staying focused and being able to deal with situations that you were not expecting. So they really try to distract you, and they're seeing how you react to that as well. It's as much a test of your technical skill as it is of your mental ability to focus. So luckily I passed that in 2022 and became a licensed pilot, but my learning did not stop there, and it will never stop learning, because being a pilot, you are constantly gaining more information and improving with each flight. And you have to be able to accept that you did something wrong and correct those mistakes. One of the interesting statistics about pilots is that the highest accident rate occurs just after a pilot becomes licensed. This is generally because pilots become overconfident without yet having the experience to justify that confidence. So you always have to be aware of that and willing to constantly learn. So some of the takeaways from flight training that I have and what I've decided makes a good pilot are actually things that apply generally to learning and life. So the first one is focus under pressure. When you're flying a plane, you have to be able to deal with a lot of external pieces of information, but you cannot let them distract you from your main goal, which is flying the plane. One of the things that instructors will tell students throughout training, no matter what happens, fly the plane. That means that if you're flying along and your aileron gets stuck or your rudder falls off, your first reaction shouldn't be, oh my God, what do I do? And like take your hands off the controls and freak out. Your first and constant reaction should be, okay, my first priority is to keep flying the plane. While I do that, let me deal with what's going on over there. The second thing is you always have to be organized, even though you do the same things every single day, every single flight. Pilots will write it down and use checklists to make sure when they're doing their inspection, when they're taking off, when they're landing, they've gone through every single thing that they need to. because one day you might forget one thing, even if you've done it a million times. So being thorough and being organized is critical for safety. Like I said, you have to seek to constantly improve. That includes listening to the experiences of others, because while learning from your own experiences is great, you don't want to have to go through an accident to learn from someone else's accident experience. And then lastly, it's more than being a pilot is more than just flying the plane. You have to also be involved in the operations of an airport. That means helping ground control. It means monitoring the weather, being aware of regulation changes, and generally watching out for every other pilot's safety. So it's very much a community activity, and it's been an absolutely wonderful experience, contributed a lot to technically what I'm interested, but also how I think as an engineer and as a person. So with that, I'll switch gears a little bit to introduce what I study at the University of Virginia, material science. So as a sort of, I won't ask just because we're on Zoom, but I want you to think to yourselves, like, do you know what material science is? Because when I went to university, I don't think that I had consciously thought of material science as a discipline on its own. And I'm sure a lot of people on this call here haven't really heard of it before. So essentially, material science is the study of stuff, which is not a very satisfying answer, but it just means that everything in the world is made of something. And the material science is the application of physics and chemistry to understand the atomic structure and microstructure of every single material, whether it be wood or glass or steel or aluminum, and understand how that underlying microstructure affects macro scale properties of the material. So in essence, why is steel hard and why does glass shatter? How can I make a material differently to make it stronger, to make it lighter? And it's interesting because the reason my degree is called material science and engineering is it combines aspects of science and research, getting to the bottom of something, understanding the why, but then the engineering is taking that why and applying it to say, okay, so what do we do now? How do we use that information to build a better material? So it's a great discipline for someone like me, and I'm sure a lot of you who are interested in science but want to do something with it. Don't just want to study something for the sake of studying it, but want to use that information to improve some aspect of industry. And in one of the really great things about material science is, like I said, because everything is made of something, you can use it and apply it across several industries. So in aerospace, you can use it to develop lighter materials to make more energy efficient planes. In the semiconductor industry, you need material scientists to figure out which materials are the best. In terms of manufacturing processes like 3D printing, welding, casting, forging, every sort of mechanism used to build something, those things affect material properties. And so material science is needed to inform those. So it's essentially, it's where the action is. It's how you can tangibly affect different components across industry. So one of the, I think, ways to demonstrate how important material science is across industries is going over what are called materials limited problems. So this is essentially a problem in society where the limiting step to us developing a solution is our understanding of materials. I'll just go through one example. There are these things, and these pictures kind of go from top to bottom, left to right. So we'll start with the top left image. This shows a diagram of what we call a wingtip vortex. So that is the tip of a wing of a plane, and a vortex is created when the air going on top of the wing and the air going on the bottom of the wing combine violently and create a swirling vortex. This happens to all aircraft, gliders, power planes, commercial jets, small private planes. And you can see on the image in the top center, it's a visualization of what the vortices look like because there's some clouds in the background and those that turbulent air has caused a pretty cool swirl looking effect. But although it looks cool, it's actually quite harmful to the energy efficiency of the plane. It creates a lot of drag, which remember is that force pulling the plane backwards. It actually contributes 1/3 of the total drag that commercial planes experience on average. So one of the solutions to this is, as you can see on the top right, it's called a winglet. And if you've recently been on a commercial plane and looked out on the wing, you'll notice that most of them are upturned at the ends. This is to minimize the size of wingtip vortices as well as move them up and away from the body of the airplane. So they do increase energy efficiency to an extent, but they don't completely get rid of the vortex. So one crazy idea that someone proposed decades ago was, if we want to eliminate wingtip vortices, why don't we eliminate wingtips and have, as you can see on the bottom left here, infinite wings or closed wings where there's no tip at all. So there's no point at which the air on the top and the bottom can recombine. This seems like a crazy idea, but it is actually quite achievable, and models have been made to show that, yeah, like you can still produce lift and you can eliminate the wingtip vortices. But why haven't we done this yet? Well, the answer is that we don't have the materials to structurally produce that shape and still be strong enough to withstand the forces that a plane experiences. So, but we're getting closer and closer. So this sort of GIF on the bottom right shows a Boeing test facility testing how flexible its wings are. And you can see we're getting pretty close to be able to turn the wing completely in and of itself. So the material advancement that is limiting our advancement to this problem is the development of flexible and yet strong materials to build wings out of. So this kind of demonstrates how material science is critical to solving a lot of really important problems. Okay, so back to a little bit about what I do at the University of Virginia. As a material science major, I've had the opportunity to get involved in a lot of different kinds of research. So I've been working at the Center for Electrochemical Science and Engineering at UVA for the past 3 years. I joined it at my first year, and we focus on corrosion. So all of you probably know corrosion as rust. You see rusty nails, rusty handles, but surprisingly, and this statistic actually surprised me, corrosion accounts for 3.4% of global GDP. So it is a big deal. Critical infrastructure around the world is affected by corrosion. Not only does it cost a lot of money, but if something like a bolt on a bridge corrodes, or a component on a ship corrodes, that can actually put human lives in danger. So what we do in the lab is study the corrosion as a mechanism and how to prevent it. So I'm going to give a little 1-minute crash course on why corrosion happens using this diagram at the bottom right. So this is a picture of a slab of iron immersed in water. And you can see an anodic side and a cathodic side, which are essentially just two different parts of the slab of iron. What's happened here is that the anodic part of the iron loses an electron, and the electron travels to the cathodic side. In order to balance this chemical equation, a positively charged ion is then released from this site, combines with oxygen from water, as we know, H2O, to form rust that is then deposited. So it doesn't need to be iron. This essential process happens with lots of metals. All you need are 2 different types of metals or 2 different sections of the same metal. You need an electron path or a conductive path for electrons to travel between these 2 metals. And you need a fluid or electrolyte through which ions can travel. So those 4 elements are all that you need for corrosion to occur. Excuse me. So my lab focuses on how do we prevent corrosion to protect structural materials. But other labs also study corrosion to be able to use it. So something interesting is that this process of corrosion releases energy And this is how we produce batteries. So for batteries, of course, we want to be able to take advantage of corrosion. Whereas for industrial applications, we want to be able to prevent it. So either way, we want to be able to understand how it works. And then depending on the application, we treat it in different ways, which I think is quite interesting. So I would strongly recommend to all of you considering careers in science and engineering to use university as an opportunity to get some hands-on lab experience. I think that you can't really know that you truly want to do something until you try it out. And so in this lab, I've been able to work on projects for various companies or government agencies and work on like real life projects with real life applications. My first year, I worked on a US Navy project studying corrosion to protect naval ships. And for the past 2 years, I've been working for the International Space Station. This is a little bit funny, but so they're having an issue currently with corrosion of aluminum in one module of the International Space Station. Their main hypothesis initially was that this was caused by a toilet leak. So for a while in my lab as an undergraduate research assistant, I got to do materials testing and tensile testing on samples that had been immersed in urine. And I was carrying around like jugs of pee everywhere. Projects are definitely, there's never a dull moment. But as an undergrad, I've been able to learn how to do sample preparation, and use really cool mechanical testing equipment, like you can see on the bottom left, and then use different microscopes, like scanning electron microscopes, to actually study the surfaces of materials. Like you can see an example of that on the bottom right. And of course, lots of data analysis and writing and presentation skills that you get from describing the work and the research that you do. So it's been a very great experience. So much so that I jumped at the opportunity to do a slightly different field of research for a summer at Imperial College London. So this is where I dove into hydrogen embrittlement. So hydrogen embrittlement is subtly different from corrosion, but it's related because it's another mechanism by which the environment can harm materials. Essentially, as you can see on this diagram at the top right, hydrogen is in a lot of places. It's in the air, it's in the water, and it's a very small molecule. In fact, it's the smallest that we have. And as such, it can seep into materials, into cracks, into pores, and create pressure at interfaces, making a structural steel, which is normally ductile and very strong. It can turn it into brittle, like something like glass would be. So for example, in a pipe, which you can see an example of here on the bottom left, if it's carrying hydrogen, then instead of bending when pressure is applied, it would just shatter or crack, which is of course not what we want, because that causes leaking and a variety of other problems. This is actually an example of a materials limited problem, or it contributes to an example of a materials limited problem. You may have heard of a concept called the hydrogen economy. This is the idea that we can use hydrogen as a source of fuel to power cars and planes. And scientifically, as a concept, not that complicated. We understand how to harness energy from hydrogen. The issue, or the materials limited problem here, is that actually holding hydrogen in vessels and transporting it through pipes is not possible, because those very pipes will become brittle due to hydrogen embrittlement. Not to mention, if you're filling up your car's gas tank with a bunch of hydrogen, then the gas tank itself would probably crack due to hydrogen. So it's very important for the implementation or application of using hydrogen as an energy source to be able to solve this problem and come up with better materials that are able to resist this hydrogen embrittlement. So as I mentioned, I did this project for a summer at Imperial College in London. Specifically, I was studying how we can use additive manufacturing, which is just a fancy word for 3D printing, which I'm sure all of you have heard of, to carefully print materials that are able to trap hydrogen and perform better in the presence of hydrogen. So this is an ongoing project. I, of course, did not solve it in one summer, but I learned a lot. It was a wonderful experience. Again, strongly recommend doing research in different labs during university if you have the opportunity to expand your skill set, as well as, you know, when you do it internationally, you're exposed to a different way of thinking, a different way of applying the scientific method, and connections to researchers from other countries. So that's always great. These are just some pictures of my time there. On the top left, these are some of the people in my lab. Also in the top right, we all went axe throwing one time. And then interestingly, on the bottom right, that is me standing in Amsterdam on a 3D printed bridge. And you can't see the whole thing in that picture, but that's actually the world's largest fully 3D printed bridge. I specifically visited it because one of the graduate students that I was working with at Imperial College London did his PhD on this bridge. So that was pretty cool. And let me just take some water. Along the way, I also was just able to do traveling while I was doing research abroad in Europe. I got to bring my brother along. In general, research is very international. It's very collaborative, and so you end up traveling to a lot of places for conferences and presentations and things like that. So here are some of the presentations I've given at UVA, at Oxford. The bottom left is a picture of me at a conference at Oxford that I recently attended. And I've even gotten the opportunity to mentor other undergraduate research projects, which is what that picture is on the bottom right. So lots of really great opportunities there. And one key thing about research is that, you know, it's very technical. You do a lot of science and math, but it's completely worthless if you're not able to communicate it to other people, if you can't tell people what you've done. So it is very important to be able to write properly and to be able to speak properly. So that is a key part of research, as well as doing the actual research. So now I come to what I'm currently working on. So this summer, I'm an intern at a nuclear engineering firm called NPR Associates, which is in Alexandria. Excuse me. This is quite different work from research. So instead of working in a lab, I am working in an office in industry, which is very fast-paced rather than you working on things that are going to be applied 10, 15 years from now. It is a client comes to you, generally in this case, a nuclear power plant. They have a problem that needs to be solved this week or next week. So it's been quite a change of pace for me. So backing up a little bit, the nuclear industry has been around in the US since the 60s. The way a nuclear power plant works essentially is radioactive fuel is put in a core, it generates heat, heats up water, which creates steam, and then this steam is used to turn a turbine and generate electricity. That is a very, very high level explanation, of course, but that is essentially what it is. We have currently 96 operating nuclear power plants in the United States. And you know, you may be wondering, well, what does nuclear power have to do with material science? Well, in a nuclear reactor, you have components that are operating at high temperatures, very high pressures, and are also exposed to all kinds of radioactive fuel and substances. So all in all, this is a very harsh environment for a material to be in, and nuclear power plants need to be able to ensure that their components can withstand this environment, and that their components are constantly monitored for signs of degradation. So it's actually a really, really good application of material science. So that has been really interesting work. The regulatory environment is also interesting. I'm sure you've all have heard of Chernobyl, Fukushima, 3 Mile Island. These disasters have happened in the nuclear industry in history, and as such, it is a very safety-conscious industry. So there are a lot of very strict regulations that have to do with ensuring that the correct materials are used in the correct places. So as I mentioned, this is very different from research lab-based work. Instead, this company is modeled as a consulting firm. So what that means is that clients such as nuclear power plants will come to us as a company with a problem that they can't solve, and then our team of engineers will get together, whether it be material scientists or mechanical engineers or chemical engineers, depending on what the problem is, to come up with a solution. And generally, it's come up with a solution within the next month, because these are all businesses. They need things to be operating in order to make money. So very different pacing than in research, where something may or may not be implemented 10, 20, 30 years from now. Another aspect of this work as an engineer is you get exposed to a lot of how the business side of things operates. You understand how different industries make money. And while that's not exactly a sort of technical engineering aspect, it's still very important and very interesting. It makes it easier for engineers to have impact in an industry when they understand how that industry works. So my last little tidbit here is, I've showed you a lot of places where I have explored the discipline of material science through my work. But your career can be more than just your job. And there are a lot of other professional development opportunities that have helped me along the way. So Material Advantage is the name of the National Professional Society for Material Science. And this is not unique to material science. Any sort of engineering or science subject has these professional organizations where professionals come together, discuss their work, share ideas, and generally network. So as a part of Material Advantage, I've had the opportunity to speak to legislators on Capitol Hill about material science and how important that is for various industries. I've also had the opportunity to tour power plants and recycling centers and generally meet other material scientists and discuss ideas. So this is a great way, no matter what field you end up in, to invest in your brain and also your network. So I would highly recommend whatever you end up doing, whether it be material science or whether it be some other aspect of science, joining a professional society will give you a lot of leadership opportunities and engagement opportunities. So what are some lessons learned for those of you who are, thinking about what you want to do in college, thinking about what you want to study? So as you can see from this fairly disjointed presentation, I have used my time in high school and college to cast a wide net. If I'm interested in something, I have found an opportunity to try and do that, to see if I really enjoy doing it or if I'd rather do something else. So that involves two things. Find something that you are skilled at doing, that you're actually good at, and that's something that you are passionate at, because you need to be able to fulfill both of those things to have a fulfilling career. For example, I might love to draw, but I'm a terrible artist, so that would not be something that I would pursue. So those two things are important, and the way to find that out is to just try many different things. So also seek varied experiences. So throughout this time, I have had the opportunity to work in academic settings for labs, but also in industry and in business, and even for government organizations like NASA. Every single place is slightly different, and some people like more than others, but the only way you'll find that out is if you go and experience that yourself. So summers in college, where you have the opportunity to do internships, are a great time to do that. And then I would say, while you're exploring things, talk to experienced people. Talk to as many people as you can, because everyone will have a different perspective. Some people will have bad advice, so you don't have to listen to everyone, but it'll help you cultivate mentors who can advise you through, when you're trying different things and ultimately have to make decisions. And then the last bullet point is probably the most important. You do have to work really hard. There's no shortcut when it comes to pursuing this applies to becoming a pilot, this applies to pursuing material science or any sort of engineering degree. You have to study a lot, you have to seek opportunities to hone your skills, and yeah, there's no shortcut when it comes to that. So yeah, so at this point, I'm happy to answer any questions about flying, about material science, or about sort of college advice, high school advice. Yeah, thank you very much.
I have a question. So, what made you first interested in gliders or flying planes?
Yeah, that's a great question. I think that I've always been fascinated by aviation. Growing up in DC, I would always go to the Air and Space Museum and things like that. I think also I was partially inspired by stories of my great aunt or great great aunt who flew Spitfires in World War II. But I think the rate limiting step for me, I've always wanted to fly, but starting at 15, that happened because that was the age at which my mother let me start flying. I asked her enough times and wore her down, and she let me start flying. And then after I started learning how to fly, my younger brother also started learning with me. So it's become a little bit of a family thing now. I see some questions in the chat, so first question is, was it scary for you to fly at first? That's a very good question. I think it's good to be a little bit scared because that makes you careful. At the beginning, you're never going up by yourself. You always have an experienced pilot in the back. So there's no reason to be scared at the very beginning. But then once you solo for the first time and then you're flying by yourself, then yeah, you are a little bit scared. But it just makes you careful, and you have to really think about all of your training. I think that you do so much training with another guy sitting in the back seat so that when you are flying by yourself, a lot of the things happen naturally and you don't have to consciously think about a lot of the decisions that you're making. So you can be a little bit less scared because you've done things a million times. But yeah, I think I can safely say that probably people like my mom and my dad were more scared about me flying on my own than I was. And then another question in the chat here, what are some of the more fun experiences of being a material science major? I think that one of the coolest parts of being a material science major is we get access to a lot of very nice equipment, nice microscopes. I think so. For example, a piece of metal, a piece of steel looks very normal when you just look at it from far away. But then when you're able to put that under the microscope, especially an electron microscope, where you're able to see things on the order of magnitude of microns, then you essentially enter a whole new world of the really, really tiny things that we can't see with our human eye. So being able to kind of enter that new world using this really, really high-powered microscopy equipment is absolutely fascinating. And when you learn about in lectures and classes about what different microstructures look like, and then you're able to find that on an actual sample, that I think is one of the most fun things. And actually, I included a picture of a sample here. Yeah. So the picture on the bottom right here is a picture of a steel sample that has been broken open. So this is what we call the fracture surface. And these red lines are me taking measurements of how long that particular gray shaded region on the sample is. As you can see a little bit further to the right, the material starts looking differently. And that's because this part of the material has cracked in a brittle way, and this part of the material is cracked in a ductile way. So the fact that there's such a clear difference there, I think is really cool. Yeah, so that's one of the really cool parts of being a material science major.
So you mentioned your summer in Harvard. How did you get interested in linguistics and anthropology?
Yeah, I think the real answer is through watching Indiana Jones movies. I always really loved Indiana Jones movies and like the archaeology aspect of using like artifacts. Although I'm well aware Indiana Jones is very much fiction, but using artifacts to understand past cultures and history, and how that ties into language and things like that. So that sort of was the initial fascination. And then I think I read a book about linguistics which talked about how words change over time, and how, for example, the like Proto-Indo-European is a language that existed, many years ago, and all European and many Indian languages have all come from that one language. And that in itself is fascinating. And then trying to piece together the puzzle of, okay, which language is related to which, I think that really appealed to me.
Is your work as an intern harder for you than the work you did in a lab?
Yeah, that's a great question. I think that the main difference, as I talked about, is that working as an intern for a company, a consulting company, is a lot more fast paced. So rather than in a lab where I'm working on one project for 3 years, when you're working at an engineering firm, I will be working on 5 or 6 different projects at the same time. But I think it probably is a little bit harder because of that. There's that added stress, but I've enjoyed it a lot simply because you can see the effect of your engineering work a lot faster. So you'll work on fixing a problem, a plant will implement your solution, and then it'll start running again. And as an engineer, I can say, oh, I actually helped that plant start running again. So I find that very rewarding. Sometimes things go wrong, sometimes mistakes get made, and then if you make a mistake, you don't have a lot of time to fix it. So again, it is quite a high pressure environment. But yeah, you do see the effect of your work a lot faster as well, which I think is cool. I in the chat, there's a question: how did you manage to get so many cool internships? I'm really glad someone asked this question, because as high school and middle school students, you must be thinking about, I want to work here, but how do you actually get these jobs? The answer is through talking to people. So a lot of internships in college, you go online, there are applications that you fill out, but the actual, at least personally, my success rate with just filling out an online application has been quite low. So the positions I've gotten in labs and this position at a nuclear power plant that I've gotten has been because I have sought out someone who works there and talked to them about their experience, and then applied after they know me a little bit. So getting my first lab position in university, I was taking a class that the professor who runs the lab was teaching. So that was the connection there. And honestly, that's a really good place to start doing research in college, is talk to the professors that you have classes with, because they know you. And then the research opportunity I got in London was with a collaborator of my professor at the University of Virginia. So I asked him for help. I told him, hey, I'm thinking about doing research abroad. Do you have any suggestions for me? And he gave me a list of people that he's worked with in similar fields and was able to recommend me to them. So again, that's an example of just talking to people. And yeah, so it does take quite a bit of effort to seek out the lab internships or industry internships that you want to do. But you have to be active rather than passive to get those positions. You have to be a little bit persistent.
What are some companies or industries that you recommend for interning?
Wow. Well, obviously, it depends on what you're interested in. So I would say that, for material science, companies like Rolls-Royce, Pratt and Whitney, a lot of these engine aerospace companies are great for material scientists because they're always thinking about materials development there. And then on the energy side, nuclear places are, again, always looking for material scientists because of the high temperature and harsh environments that materials are exposed to in nuclear power plants. So that's sort of like a materials perspective of things. Broadly speaking, when you're thinking about companies to intern for or research experiences to do based on what you're interested in, I think company-wise, you have to consider how big the company is. So like a huge company like GE or Boeing, you may have a very different experience than working at a smaller company like NPR, where I work now. And you may like the bigger company better, you may like the smaller company better. I think smaller companies, you probably would have, you would know like know a lot of your colleagues a little bit more, and be a little bit more involved in like the business aspects of the company. Whereas in a big company, you might have access to more resources. So there are trade-offs there. And so yeah, sorting into big and small companies, I think would be good, but obviously specific names of companies depend on what you're interested in doing.
Do you have any recommendations for where we can get flying lessons?
Yeah. I mean, it depends on where you live. So I guess where are you local to sort of the DC area, or are you?
Yeah.
Yeah. I mean, so for the DC area, I think the closest glider club for me was near Gettysburg, Pennsylvania. But you can look up online where your nearest glider club is. There are far fewer glider clubs in the US than there are regular airports, as you may imagine. So you may have to travel further away to get to a glider club. I believe there's one in Front Royal, Virginia as well, so that might be closer depending on where exactly you are. But then there are many more power airports in the DC area and across the US that sort of, if you want to start with power flying, which you can, that's also an option. But I think if you're starting out flying is a relatively expensive hobby. So I think it's good to start with gliding because it is slightly cheaper. You don't have to pay for instruction. You don't have to pay for gas. And that way you can figure out, again, like if you like it or not before you actually put in the investment to fully commit to that. So yeah. I've gotten a question in the chat saying, when applying for an internship, is it based on skill or age? I wish I knew exactly what these companies were thinking when it comes to accepting people. I think generally, like when you're in university, sometimes internships will be geared towards a specific year in university. I think a lot of the times this is because they're trying to get you back full time. So they want people who are in their junior year or their sophomore year so that they can keep them until they graduate. But otherwise, I think it's mostly skill based. When you're even in high school and in college, I'm sure you'll generate like a resume with all of your experiences and your skills, and you know, your grades and classes are also important when it comes to being hired for internships as well as lab experiences. So yeah, I think a little bit of both, but hopefully, depending on the place, mostly based on your skills, but also your interest. You can be really smart, really good at things, but I don't think someone's going to hire you if you're not actually interested in them. Yeah.
Do you have any advice for high school students who are still looking for a major or undecided?
Yes, absolutely. I think going back to just casting a wide net, if you try and seek out many different varied experiences related to things that you could be interested in, actually doing things will really quickly give you an idea of whether you like something or not. So in high school, you know, take classes, take electives that are interesting to you and see if they're actually still interesting to you. Go to like fairs. If you're interested in science, there are a lot of outreach events that you know, you can talk to people who work in a field that you may be interested in to see, ask them about what their day-to-day work is like, what they did to get to that point in their career. So that again goes to talking to as many people as you can, seeking out mentors. I think those are the best ways, hearing other people's experiences as well as trying to get as much different varied experience yourself. It's the best way to make a decision. But also know that when you come to college, you can change your mind, especially if you're doing some sort of science or engineering, just STEM in general. A lot of engineering degrees at the beginning are quite similar. So, you know, I came in being an aerospace engineering major, and I took a class that talked about material science and suddenly decided, oh, I'm actually going to do this instead. So don't panic is another piece of advice.
Around how many years of flying experience do we need to get a license? Or does glider experience give real flight piloting experience as well?
Yeah, so I think that the amount of time it takes to get a pilot's license is less measured in years as it is in time that you are actually flying. So one of the issues with my training experience is that, you know, COVID happened in the middle of it, so that kind of stopped me from doing training, as well as other school commitments. You know, applying to college took a lot of time. So there were several points throughout my flight training where I couldn't fly for a few weeks, and that definitely slowed down when I was able to progress through the process. So some people can get their pilot's license in a summer. If you're flying every day, you can get your pilot's license in like a month. It just depends on how much time you spend on it, rather than just the time since when you started, because it's a very practical skill. If you go a long time without practicing, then you have to kind of make up some of the time that you lost there. So yeah, it can take a month, it can take 10 years. It depends on and one little tidbit of information. I think this applies quite generally as well, but when flying a plane, it's often noted that younger people pick it up much faster. So learning as an adult, I think generally takes a little bit longer time rather than instead of learning as a teenager. Actually, so I've been flying since I was 15, but my younger brother is even more impressive. He got his license before he got his driver's license. He got his pilot's license before his driver's license. So young people do pick up things very fast. And then your second question, so glider flight experience versus engine flight experience. When you get a pilot's license, that applies generally. So you have a pilot's license and it's called the same thing, whether it's for helicopters, for powered planes, for gliders. The difference is you get different ratings based on what type of aircraft you're able to fly. So for example, for me, I have a pilot's license with a glider rating. And if I wanted to also get certified to fly a power plane, then it would be a lot easier for me because I already have my pilot's license and I have that aerodynamics knowledge. But I would do power training and then just get a rating added to my pilot's license.
Do you recommend studying abroad during college?
Yeah, I think my answer would be yes. I think studying abroad is a great way to be exposed to different ways of thinking. I opted to, instead of studying abroad, just work abroad because I thought that conducting research would be a little bit more valuable to me than just taking another class in another country. But of course, it would depend on you know, your major and what you were pursuing in college. I think one of the things is that for engineering and a lot of science subjects, it's a lot more difficult to study abroad just because you have so many more requirements in college, but it is still possible. And what I did is I just did it over the summer. So if that's an option for you to do study abroad over the summer or work abroad or research abroad, I think that's a good time to do it. It was working abroad for the summer. And then I've kind of remained in contact with the group in Oxford because we're working on writing a research paper, and I attended a conference in June, and I'll be attending a conference with them in September as well. So it's been over a year since I started working for them, but I'm no longer working full time for them. Obviously, the full time was just over the summer.
It seems we've reached the end of today's webinar. I would like to thank Lara for graciously joining us to speak about material science and aviation. Thank you so much for sharing your insights and knowledge with us today. I would also like to thank everyone for joining and participating in today's session. We hope you all we hope you all enjoyed it and learned something new. Thank you once again, and please stay tuned for the last upcoming webinar in our STEM series next Sunday at 5 p.m. on Zoom. We also have a personal items drive for a homeless shelter in Northern Virginia next Saturday at the KCS volleyball tournament in Virginia. We have additional locations if you would like to drop off items between tomorrow and the 31st. Thank you.